Alright guys, we've been on the road about 10 hours. We filled up once just outside of Phoenix, and even Bon Jovi is getting bored now. So let's talk about something. 5.3 is pretty much in its own. We're cruising just over 75, maybe 77, 1800 RPM. We've gone 180 miles on the first quarter of a tank. Well, just over a quarter of a tank since we filled up. So let's come back to our dash deck. I don't know if you can see this. Look at the big dial in the center. That's MAF frequency. You're going to see a blink out because this dash deck right now is set up for both generic OBD2 and GM specific, and they kind of clog up the CAN bus, and you'll see it drop out. But when you do see it up there, 5,000-6,000 hertz, that's actually frequency hertz. That's measuring airflow, and what's important about that is GM operating systems have been dependent on mass airflow sensors for a lot of years, and I think they have some significant advantages. Measuring actual airflow using a MAF sensor is superior to using speed density, which means you're running off an intake manifold vacuum through the MAP sensor. Of course, the GM motors have both, the MAP sensor and the airflow meter. Basically, there's a wire inside of the MAF sensor that warms up, and as the air goes past it, it measures the amount of current that needs to be supplied in order to keep the wire at a certain temperature. They're kind of expensive sensors, and that's one of the reasons Chrysler doesn't use them. In the early days, they had problems with the bulbs getting plugged up with dirt and contamination, especially the Fords. Some of them tried, excuse me, some manufacturers tried putting burn-off relays or burn-off coils in, that when you turn the key off, it would get the wire red hot and burn off any contaminants, and that caused its own problems. But modern MAFs are pretty reliable and very, very accurate. When you look at the scale here, you want to see a nice smooth airflow. If you see that needle jumping around, it probably means you have a problem in the intake tract. Maybe you have a snorkel that's causing an oscillation, a plugged air filter. MAFs are very sensitive. What MAFs can do is measure air density. Not so much air density, but as you change altitude, the MAF will compensate for the density of the air. With a speed density based system, you're basically running off an intake manifold vacuum, and that can really vary based on engine operation, how old the engine is, and other environmental factors. Where the MAF is always going to measure actual airflow versus calculated airflow, and it gets kind of complex, but I believe running on the MAF is superior for everyday driving around and efficiency. Plus, it's redundant. If the MAF were to fail in a GM operating system, it would revert to the MAP. It would go speed density. With the Jeep JK and most other Chrysler operating systems, they won't use a MAF. They don't use a MAF, and solely basing the calculations on the MAP sensor work fine in a perfect world. If you took a one-bar Chrysler operating system like the JK has and tried to bring it to a 2 or 3 bar system for, let's say, a supercharger or a turbocharger, that's really where the lack of a MAF can come into play, because, as you know, a supercharger compresses the air beyond atmospheric. So once you go past 1 bar on a speed density system, you're completely dependent on intake manifold vacuum for all your calculations. Chrysler uses a predetermined airflow table that they put into the calibration, and the supercharger tuners and turbocharger tuners do their best. They use offset maps. They try to put essentially a 2-bar map into the system, but it's very difficult to integrate it to a level that drivability is equal to a normally aspirated engine. You're going to have surging, you're going to have dead spots, flat spots, hesitations. In cruise control, you might notice some fluctuations, and running on the MAF really has advantages, and the GM operating systems, almost all of them run on the MAF. They're very, very sensitive devices, and if they go out of range, it will revert to a speed density system, just like the JK has. And I think there's a certain amount of security with that. But when the MAF is working properly, you'll find that the power delivery is smoother, that you will have less fluctuations from altitude. So if you go from sea level to 8,000 feet, 9,000 feet in one ignition cycle, where on a lot of speed density systems like the JK, when you turn the key on, it takes a baro reading off the map sensor, which tells it basically what the altitude is or the atmospheric pressure is. And then it uses that for its calculations after you start the motor. Some systems use a separate baro and map, so it can monitor the atmospheric pressure as you go up and down in altitude, and that's obviously better. Some of the GM systems have both a baro and a map, and that's the best. But with a MAF sensor, you're going to see less drivability issues at high altitude, low altitude, cold temperatures, hot temperatures than you will with a speed density system. For racing or high performance engines, a lot of guys like to ditch the MAF because not only does it add complexity, but a restriction in the exhaust, and it's just not needed. So you probably don't want to run a MAF for a track vehicle. But in the real world, for everyday driving with your family in the car, off-road, when the weather's crappy outside, I think you'd be better off having a MAF than not. So that's one significant advantage between the LS, the Hemi, and the 3.8 is the operating system is based off of actual airflow versus calculated, and the LS has the ability to run both in a speed density and a MAF mode, and that really is a significant advantage. Let's look at this screen one more time, and you can see on the left the long-term fuel trims, and on the right the short-term fuel trims. You notice the short-term fuel trims are moving around quite a bit. They're making calculations many times per second, while the long terms are basically using the short terms to change the fuel adaptive. So if the short terms are constantly negative, in the long term trims will start pulling fuel out of the base calibration, and it will store that information until it's cleared or the battery's disconnected. So you get the best performance for the fuel you're using, the temperature outside. There's so many variables that go into calculating the actual fuel flow, and the long-term fuel trims are a key part of that. So if you ever want to monitor how your operating system is working, look at your long-term fuel trims. With a GM system, the long-term fuel trims mean a lot because we are based on actual airflow, and the operating system knows with X amount of air entering the engine, X amount of fuel should be entering the engine, and it's a very close relationship. If it gets out of that relationship more than 15, 20, 25%, let's say it hits 30%, it will know something is wrong and go into a limp mode, base its calculations on the map sensor, O2 sensors. It might even revert to the we got a 45 mile an hour speed zone here. Yeah, it's so easy to cruise in this thing at 75, 80. You don't realize. I mean, I'm going 50, and it feels like I could get out and walk. Getting back to the map and the MAF, the system will know, based on the amount of air coming into the engine, how much fuel it should be putting in. And if it gets 20, 30, 40%, well, not 40, it'll never hit 40. Before you hit 40%, it would go into a limp mode, and you probably throw a 171, 174, 172, 175, lean or rich limit reached, bank 1, bank 2. And what that means is the computer tried to correct as much as it could based on the airflow coming in, and it couldn't. So it rejects the MAF sensor signal at that point and goes into a limp mode. And that's a good mode to have, because if you had, let's say, a major vacuum leak, your PCV valve came out, or had whatever, the system would allow you to continue to drive in this limp mode. And with a speed density system, without having the MAF, you're running on calculated airflow. So if you were to have a failure, you wouldn't have as many options available, and you possibly would have to stop. Where with a GM operating system, you may be able to continue. So that's probably more than you wanted to know about MAF sensors and speed density. But all the LSs that we do have MAF sensors, and they're calibrated for the engine. And I believe in the long run, it makes for a smoother, more efficient, and cleaner engine. And this engine has well over 100,000 miles on it, and it just required its emissions test. And of course, there's no codes. In fact, let's go here. We'll go to diagnostics, read codes. You can see we have no codes, and this ECM has not been cleared. I can't remember. It's probably been years. I would guess to say that the hydrocarbons in this engine are less than 20 parts per million, and COs are close to 0, maybe 0.05, which would pass new car standards. And this engine has well over 100,000 miles on it. There's no misfires. There's no oil usage. It's just a bulletproof engine, and the millions and millions of Chevy trucks and SUVs running around with this engine, while not the best performing SUVs, I believe are some of the most reliable. We have these 5.3s come in the shop all the time, work trucks, 250, 300,000 miles, and we're replacing radiators and axles. We're doing an axle job on one right now, and the engines just keep going. So it's a great engine, and I would expect to have at least twice the longevity out of this 5.3 than out of a 3.8. And at this point, I would venture to say 3 times the longevity from a 3.6 Pentastar. I think the Hemi is probably better than the Pentastar at this point, longevity-wise. I really don't know. I've seen Hemis with 200,000 miles on them. They do tend to require water pumps and other. They have a lot more parts than the LS has. Of course, they're both overhead valve, but the Hemi has a more complex valve train, so it has more parts. So really, I think the winner in reliability and longevity is going to be the LS, and it's proven that for a couple of decades now. So we're going to continue on. We're going through, I think this is Tucson. We're going to hit New Mexico, and then hopefully be in Texas tomorrow. Ironically, when we hit El Paso, which is the eastern edge of Texas, we're about halfway there. So we're going to go across 3 states to get to Texas, and we're only halfway there. That's how big Texas is. So from El Paso to Houston will be quite a drive, and we'll hopefully see you soon.